Okay, let us start the lecture. Today, in this lecture, we will discuss Riemann integration, and then we will see the relationship between Riemann integral and Lebesgue integral. Okay, so this is Riemann integral. The name of the title of the section is Riemann integral as a Lebesgue integral. The Riemann integral, this is the last section of this unit. The Riemann integral as a Lebesgue integral. Throughout this section, the function f will be a bounded function on closed interval a,b,r. Throughout this section, f will be a fixed bounded real valued function. Throughout this section, f will be a fixed bounded function okay, on closed interval ab, on a closed interval ab, on a closed interval ab, into this set of real numbers, okay, R. So that is this f is a function from a, b to r, and it's also bounded. So हमें एक्चुअली रीमान इंटीग्रल को हमें डिफाइन करना है. ये आपने ऑलरेडी किया भी होगा एनालिसिस की कोर्स में. एनालिसिस थर्ड में आपने शायद किया होगा. So first we define the partition. A collection of points P a collection of points P which is equal to this set. First point is A, okay, A equal to x naught, then x1, x2, xn, which is equal to b. This collection of points is called a partition of, is called a partition of interval a b if this a is equal to x naught, less than x1, less than x2, less than xn, and which is equal to b. If this thing holds, every partition, this partition it will divide. Suppose अगर आपका m2 लोगी, it will divide this interval into two sub intervals, x0 x1 to x1 x2, okay, if n is equal to 2. So every partition P which is a equal to x0 x1 xn equal to b divides of AB, right here, of AB, it divides AB, okay, divides this AB, closed interval AB, into n closed sub intervals, into n closed into enclosed subintervals. First one is x0 x1, second is x1 x2, and the nth interval is xn minus 1 xn. So now we can find out the length of each subinterval and the maximum length. We can always choose the maximum because it's a finite. Actually we have only finite lengths. This first length of the first interval, okay, length of second, and the length of the nth interval. So we have finite number of lengths, so we can choose the maximum length among those finite lengths. And that maximum length, because this is these intervals, they arise due to the partition P, so the maximum length will be called the mesh of the partition P. Okay, so the length of the largest of these subintervals, the length of the largest of these subintervals is called the mesh of P. Is called the mesh of P. Mesh of P, and is denoted by mod of P. And is denoted by mod of P. कुछ लोग इसको नॉर्म P भी कहते हैं, नॉर्म P भी, कुछ बुक्स में नॉर्म P से भी इसको डिनोट किया गया है. So that is mesh of P. It's actually the maximum of the lengths. Okay, it's xi minus 1. We don't need mod here because xi is greater than xi minus 1. For 1 less or equal to I less or equal to n, or you can simply write its maximum of xi minus 1 with 1 less or equal to I less or equal to n. So that's the mesh of the partition P. आप एग्जाम्पल ले सकते हो इसकी mesh, किसी भी given partition का आप mesh निकाल सकते हो. So let's take this interval I equal to the interval say 0 to 2, and let P is equal to, the first point is 0, so let's take the second point, say 1 by 2, then take the third point 1. Okay, then you can take then you can take let's take let's take this point greater than 1, let's take 7 by 4. Okay, and then take 2, right? So take this partition and let P with the partition. Obviously it's increasing, these points are in increasing order, 0 less than 1 by 2, 1 by 2 less than 1, less than 7 by 4, less than 2. So it's a partition, is a partition. You can take any number of partitions of this interval. Let's take one of those partitions. This is the partition of 0 to interval. Now let's find the length of each subinterval. Now what's 1 by 2 minus 0? It's equal to 1 by 2. The first interval, and second is 1 minus 1 by 2, that's equal to 1 by 2, and third is 7 by 4 minus 1, that's equal to 7 minus 4, it's equal to 3 by 4, and then we have 2 minus 7 by 4, it's 8 minus 7 by 4, 2 minus 7 by 4, so you can write this 2 as at 8 by 4, 8 minus 7 is 1 by 4, this is equal to 1 by 4. So which one is the largest number? I think 1 by 2 is the largest. 1, not 1 by 2, 3 by 4. 1 by 2 is less than 3 by 4. Okay. So clearly this mesh of P is equal to 3 by 4. So given a partition, you can always find its mesh. Okay, the largest length of subintervals. Now next we define the refinement of a partition. A partition P is said to be finer than is said to be finer than the another partition QC. Q, okay, of AB, both are the partitions of AB. If finer means if it contains more points, okay. If Q is contained in P, when P contains more points, holds. So now if P and Q are partitions, then P union Q, and this P is also called the refinement of P is also called the refinement of Q. If P and Q are partitions, suppose they are partitions, then P and Q, it contains both P as well as Q. Then P and Q, it is finer than both P and Q is finer than both P and Q, and it is called the common refinement of P and Q. It's called common refinement of P and Q. Now let's define some numbers, small mi, capital Mi. So we want to define lower Riemann sum and upper Riemann sum. So for this we first define some real numbers. So for a partition P of AB, let's define following. For a partition P, which is equal to x0, x1, xn of AB. This is a partition of AB. So let's define following. Let small mi, it is the infimum of mod of it's the infimum of f of x, where this x belongs to the I subinterval xi minus 1 xi. So this f is bounded function on the closed interval AB, and this one, it is the subinterval of closed interval AB, so it is also bounded here. So we can find the infimum of this function over that interval, and we can also find the supremum as well, because function is bounded. It's supremum of f of x such that x belongs to xi minus 1 xi. This is for I equal to 1 to n. Okay, I runs from 1 to n. So after this we define the lower sum of f corresponding to the partition P. and the upper sum. The lower sum of f corresponding to the partition P that you had defined above, to corresponding to the partition P is defined by S let's read it as S lower star, okay, S star FP. It's equal to sum of these MIs then into this product of the lengths I runs from 1 to n, and the upper sum is defined by, now let's define upper sum. It's S upper star FP, and that is summation. So instead of small mi we take here capital Mi, which is the maximum, which is the supremum of f over I sub interval, then xi minus 1. ओके इसको आप एग्जाम्पल से भी क्लियर कर सकते हो. सो लेट्स टेक दिस एग्जाम्पल. So let's take this function at f of x equals to, say, we are right here, say it is x squared, where x belongs to the interval, say 0 to any number, 0 to 5, say for instance 5. Okay, so it's a function like this. Its graph is like this: f(x) equal to x squared. So for x minus and plus, it's symmetric with respect to x. X is actually not. It's symmetric with respect to y axis because it's a even power of x. If I take minus x, so f x will be same as f of minus x. So the graph is like this. So here we are dealing with only positive numbers, so it's like this. Okay, it's like this. So suppose this is 0 and this is, say, 5. Okay, let's do it like this. It's a vertical line here. It's very difficult to draw this line. Okay. So this you can check. This is 0 to 5. Okay, 0 to 5. This is the graph, and you want to find the upper sum and the lower sum of this function with respect to any partition. So let's take this partition. Let's take this partition. Let's take the simple partition. Okay, take the 0, 1, 2, 3, 4, and 5. Let this be the partition of it. Partition of 0 to 5. Okay. Then what small m1? It's the maximum of the function f(x) over the first interval 0 to 1. So then what's m1? It is minimum. Okay, it's the infimum of f of x, where x belongs to the first interval 0 to 1. Okay, so it's infimum of what's f of x? That's x squared, and x belongs to 0, 1. So what's the minimum of this over this interval? That's equal to 0. And then you can find m2, which is infimum of x square. Function is x square here, and the next interval is 1 to 2, that's equal to 1. इस तरह से अगर आप m3 निकालोगे वो 2 आ जाएगा, m4 अगर आप निकालोगे that will be 3 and m5 will be 4. And let's find capital M1. So that's maxima actually, that's the supremum of fx over the interval 0 to 1, which is equal to 1. You can easily verify this. M1, M2 is 2, M3 is 3, M4 is 4, and M5 is 5. Now let's find S lower star. Now S lower star of this function f with respect to that particular partition, it is the product, it is the sum of these products, m1 into the length of the first interval, that's 1 minus 0, plus 1 into the length of the second interval, that's 2 minus 1, then 2 into length of third interval, 3 minus 2, then it will be 4 times length, sorry, it's 3 times, okay, 3 times length of the fourth subinterval, and then that's 4 minus 1 plus 5 times length of the fifth subinterval, and you can see this is 0 plus 1 plus 2 plus 3 plus 4, okay, plus 5, it's a 4 at the end, okay, it's 1 plus 2 plus 3 plus 4, that's 7 plus 2 9, that's 10. इसी तरह से आप S upper star निकाल सकते हो in front is, and that you can see easily it's equal to 1 plus 2 plus 3 plus 4 plus 5, so it's equal to 5 plus 4 9, 9 plus 3 12, 12 plus 2, what's 12 plus 2 14, 14 plus 1 is 30. So this is upper Riemann sum, and upper, you can say upper sum and lower sum. So these are the points, so this is 1, this is 2, then 3, then 4 and 5, so these are the so actually this is a upper Riemann sum. Upper Riemann sum means you are taking the supremum, and first you are taking the infimum, that's this area, then you are taking the infimum m1 is 0, so 0 into this length, so that's the area of this point actually, which is equal to 0, and then you are taking next infimum of over this area, that's 1, which is this rectangle, okay, this one. So this is the area of this line plus area of this rectangle plus area of this rectangle plus area of this rectangle plus area of this, that's the lower sum. इसी तरह से जब आप अपर सम निकालोगे, you first find the maximum of these two, maximum fx over the interval 0, that's 1 into length of the interval, that's 0 to 1, which is equal to this thing. Let's see. This rectangle, then this one, then this one, then this one. So we have two rectangles actually, two rectangles, so you are adding these areas of these rectangles, you will get the lower sum and the upper sum. And if you increase the partitions, this lower sum, it will increase and the upper sum will decrease, and if you are going to increasing these points, and you will ultimately you will find the area under this curve, the exact area of the function is integrable, okay. So if you add the points, add the partition points, you will see that the lower sum will increase and the upper sum will decrease, and finally you will see that this sum, lower sum and upper sum, they will both coincide, okay. Lower sum increases, upper sum decreases, and if this happens, if they will coincide, then we say that the function is integrable, and that the value will be the area under this curve actually. Okay, but you will see that this upper sum जो है, it's always greater or equal to the lower sum. So you can always see this. You have here you have lower sum is 10 and the upper sum is 13. So 10 is less than 30. But in general, it is also true for any function f, bounded function, and for any partition p. This upper sum is always greater than lower sum. This is true. So now let's see the first theorem. For any partition P of AB, this lower sum is less or equal to the upper sum. Okay, for any partition P of AB. Proof. तो ये भी आपने किया होगा अगर अपने एनालिसिस का कोर्स जो किया होगा आपका एनालिसिस थर्ड में. दिस इज ऑलवेज ट्रू. आपने शायद वहां पर यूपीएफ और एलपीएफ नोटेशन यूज की होगी. सो लेट्स टेक अ पार्टीशन. लेट पी बी द पार्टीशन of AB. So then, as we had defined, Mi is the infimum of or ith subinterval of F, and this is the supremum. Okay, so Mi is less or equal to Mi always. So let's multiplying throughout by positive number. Let's multiplying throughout by the length of ith subinterval, which is a positive number. This will always be less or equal to. So this is true for all I runs from 1 to n. So this one for all I equal to 1 to up to n. So adding these, you will see this is equal to summation mi xi minus xi minus 1. I runs from 1 to n less or equal to summation I runs from 1 to n capital Mi xi minus xi minus 1. So but this one, it's the lower sum, s lower star fp less or equal to s upper star fp. Okay. So in the next theorem we will see that we already discussed with you. If we increase the partition points, the upper sum will decrease and the lower sum will increase. That's actually the next theorem that we will prove here. Okay, so next theorem. If a partition P is finer than another partition, it means that it contains more points than Q. If a partition P is finer than a partition Q, that is Q is subset of P, then this lower star, it will increase. Okay, lower star of F with respect to the partition Q is less or equal to lower star of F with respect to the partition P, because P is finer, P contains more points, so it will increase, but upper sum will decrease. So upper sum of this partition, which is finer, upper sum of F with respect to the finer partition is less or equal to the upper sum of with respect to the partition Q. Since P is finer than Q, so we assume that P contains 1 point more than this Q. So if it contains, say, it may contain more than 1 point, but suppose it contains 1 point, which is not in P, So Then for the rest of points you can apply the same procedure. If it contains 3 points more than the partition Q, or 4 points more than the partition Q, the similar procedure you can apply. Okay, so we show that first we show that this thing, okay, or can prove this one, and then the second follows are similar lines. Prove. We show that S lower star FQ is less than or equal to S lower star FP. The other inequalities can be proven in a similar manner. The other inequality can be proven in a similar manner. In a similar manner. So let assume that this P has only one more point. Assume that the partition P has only one more point C T. It has only one more point CT than Q. तो P में एक ही एक्स्ट्रा पॉइंट है Q से. Let's suppose that point is Q. Okay, that point is T. Okay, so then this P P the given partition. So let's assume that let's take this partition. Okay, let Q be fix this partition Q. Q equal to say x0, x1, x2, so on, xn be the partition of intro AB. Now since P contains one more point than Q, so that point may be somewhere in between. So there is some key. Then there exists key such that 1 less or equal to k less or equal to n, k ऐसा होगा, and this point lies between these two. तो या तो ये k यहाँ ही होगा, x0 और x1 के दरमियान होगा, t पॉइंट जो एक्स्ट्रा पॉइंट है p में, या ये t पॉइंट x1 और x2 के दरमियान हो सकता है, क्योंकि एक्स्ट्रा पॉइंट है ना. एक तो p में एक सारे पॉइंट्स है और उसमें एक्स्ट्रा पॉइंट एक है t, तो वो या तो किसी न किसी जगह तो होगा वो पॉइंट. तो आपने सपोज ये पार्टीशन ली है इसकी ए बी की, आपने पार्टीशन ली है. दिस इज x0, देन वी हैव x1, देन वी हैव x2. इसी तरह से आपके पास है ये xn-1, सो देन दिस इज हियर xn. तो ये पार्टीशन p है जो आपने ली, पार्टीशन q सॉरी. अब p पार्टीशन में एक पॉइंट एक्स्ट्रा है इन पॉइंट्स को छोड़कर, तो वो पॉइंट किसी ना किसी जगह तो होगा. assume that point is here, say, and it lies between these two points xk-1 and xk-1 and xk. They are the partition points of q, and they are also the partition points of p. p में q के सारे पॉइंट्स है और एक पॉइंट एक्स्ट्रा है, that's ct. So this thing hold. Okay, there is some k with 1 less or equal to k less or equal to n such that xk-1 less than t less than xk less than xk. So जो पार्टीशन q है आपके पास, उसके लिए तो ऑलरेडी फिक्स है ना नोटेशन. mi is the minimum, supremum, infimum of fx over I sub interval, and capital Mi is the supremum. Okay, small mi is the infimum. But this then this q is equal to, then this partition p क्या होगी, it will change. Okay, it's x naught x1 और बीच किसी जगह कोई पॉइंट एक्स के माइनस वन है, फिर इसके बाद टी पॉइंट है और इसके बाद एक्स के है, देन द सिमिलर पॉइंट्स होगी जो क्यू के पास है. तो ये तो है ही इसका. Over the first interval x naught x1 the infimum is m1, and over the second interval infimum is m2, but over this interval and over this interval we have to choose the infimum, and over the k sub interval this xk minus 1 xk of the partition q, the infimum is already fixed, that's mk. Okay, so let's fix the infimum for these two intervals. Okay, for these two intervals let c1 be infimum of f of x over the interval where xk minus 1 less or equal to x and less or equal to t, and c2 it is the infimum of f of x where t less or equal to x less or equal to x k. But what's mk? But mk is like this. Mk is the infimum. That's already, the notation is already fixed. It is the infimum of fx over the k sub interval where x k minus 1 less or equal to x less or equal to x k. तो यहाँ से ये पता चलता है कि mk जो है इसका जो रेंज है ना, जिस पर आप रेंज आप इसका जो रेंज ले रहे हो ना ओवर दिस इंटरवल एक्स के माइनस 1 टू एक्स की इस ज़्यादा है इन एज कम्पेयर टू दीज टू, क्योंकि इसका रेंज एक्स के माइनस 1 से लेकर टी तक है और इसका रेंज है टी से लेकर एक्स के तक, और इसका रेंज है जो आपके पास वो एक्स के माइनस 1 से लेकर एक्स के तक, इसमें ये दोनों रेंजेस आ रहे हैं. तो एम के जो इन्फिमम ले रहे हो आप ये उस सेट का इन्फिमम ले रहे हो जो बड़ा है इन दो सेट से, C1 और C2 का जो इन्फिमम ले रहे हो, जिन सेट्स का आप यहाँ पर इन्फिमम ले रहे हो, दीज टू सेट्स आर स्मॉलर देन दिस सेट वेयर यू आर टेकिंग द इन्फिमम ऑफ एफ ऑफ एम क्यू. ओके, so therefore we must have mk must be less or equal to C1 and mk is also less or equal to C2. So this is understood. Because mk is the infimum over the bigger set, and C1 and C2 they are the infimums over the lower sets, or the smaller sets, over the smaller sets. So mk must be less or equal to C1. अगर सुप्रीमम यहाँ पर होता है उस केस में जो कैपिटल M के होता है that will be greater or equal to C1 and capital M K also will be greater or equal to C2, because in that case you are taking what? You are taking the supremum actually, and supremum will increase if the set will increase, but infimum always decrease if set will decrease. So now let's compute the lower sum and the upper sum now. Okay, let's compute those two numbers. So let's first compute the lower sum of f with respect to the partition q. q तो ऑलरेडी फिक्स्ड पार्टीशन है, इसके लिए तो वही लोअर सम है जो ऑलरेडी आपने डिफाइन किया है. अब इसको आप एक्सपेंड कीजिए. इट्स m1 x1 माइनस एक्स नॉट, और आप के स्टेज पर जब आप पहुंचे इट विल बी एम के एक्स के माइनस 1 देन माइनस एक्स के प्लस द लास्ट वन एम एन एक्स एन माइनस 1 माइनस एक्स एन. Okay, you can subtract t and add t to this kth sub kth this length, okay, length of k sub interval. Here it's m1 times x1 minus x0 plus mk times, you can write it as xk minus 1 minus t then plus t minus xk. Okay, it is not correct here. You should write first xk then xk minus 1. Okay, Okay, this is here xk minus 1, and here you write here xk minus t plus t minus xk minus 1 प्लस रेस्ट ऑफ द पॉइंट्स। उसके लिए तो वो तो सेम पार्टीशन पॉइंट्स है, वहाँ पर आपको चेंज नहीं करना है। ओके, सो दिस इज इक्वल टू m1 टाइम्स x1 minus x0 plus mk times xk minus t plus again mk times t minus xk minus 1 plus mn times xn minus 1 minus xn. Now this mk and this mk, they are less or equal to c1 and c2. So first we will see right here c1, because this because c1 is the infimum of x over the interval t to xk. Okay. Xk minus 1 to tk, that's c1. Okay, xk minus 1, so here it is c1. Okay, because c1 is the infimum of f of x over the interval xk minus 1 t, and c2 is the infimum of the function f of x over the interval t to xk. So both are mk is less or equal to c1 as well as c2. C1 as well as, so first of all I will change the order, actually that's very important. It's m1 x1 minus x0 plus mk. First you write here t minus xk minus 1, then mk times it's xk minus t plus mn xn minus 1 minus xn, and this one it's equal to, now it's less or equal, in fact it's less or equal to m1 times x1 minus x0. This mk it's less or equal to c1 times t minus xk minus 1 plus c2 times xk minus t plus mn times xn minus xn. अब देखिए, अब जो ये पॉइंट्स है ना x0 x1 x2 x0 x1 x2 so on, then xk minus 1 t, then t xk, then so on x, they are the partition points of the partition p, और ये है वही infimums over those sub intervals. Okay, so it's less or equal to, by definition it's less or equal to s lower star pf. Okay, not lesser, it's exactly equal. In fact, it's equal to this. This one is equal to. That's the definition of lower sum. So thus we have this s lower star fp fq is less or equal to s lower star fp. So similarly, you can see the same result for upper sum. मतलब वहाँ पर डिक्रीज होगा. ओके, वहाँ पर अगर आप पार्टीशन को इंक्रीज करोगे ना, फाइनल पार्टीशन जो होगी उसका जो अपर सम वो कम होगा एज कम्पेयर टू दिस पार्टीशन. So that proves this theorem completely. Now in the next theorem we'll see that if you take any two partitions, upper sum will never decrease and lower sum will, upper sum is always greater or equal to the lower sum. अगर आप different partitions भी, same partitions में तो आपने दिखाया, अगर partition एक ही होगी, the partition is the same partition, then s star of pf it's always less or equal to s star of this s upper star. Sorry, तो ये आपने बताइए, तो पहली आपने किया है, फर्स्ट जो थ्योरम आपने है वो आपने यही की है. अगर पार्टीशन सेम होगी तो ये हमेशा ट्रू है. बट यू विल सी दिस मोर स्ट्रॉन्ग रिजल्ट, एस पी एफ इज ऑलवेज लेस और इक्वल टू एस स्टार क्यू एफ, और पी एंड क्यू आर एनी टू पार्टीशंस आप यहाँ कोई भी पार्टीशन लीजिए, यहाँ कोई भी पार्ट, ये सम कभी भी इस सम से बड़ा नहीं होगा. अपर सम इज ऑलवेज बी ग्रेटर और इक्वल टू द लोअर सम फॉर एनी टू पार्टीशंस P and Q. That's our next theorem. And the proof follows from previous results जो आपने अभी किए, जो आपने अभी दो थ्योरम्स किए, इन्हीं से इसका प्रूफ आ रहा है. Theorem. For every partition P and Q, for every partition P and Q, we have, for every partition P and Q, we have this lower sum is always less or equal to the upper sum. Prove. So let's take the common refinement. Okay, so let's take this common refinement. Okay, so let's start with this. Since P union Q is finer than P as well as Q is finer than P and Q, so therefore by above theorem, अब उसका नाम 2 रख, आपने अभी तक 3 ही थ्योरम्स किए ना, दिस द थर्ड थ्योरम, इसका नाम 3 रख दीजिए. इससे पहले जो थ्योरम इसका नाम 2 और उससे पहले जो आपने रिजल्ट किया थ्योरम की उसका नाम 1 रख दीजिए. इट्स फ्रॉम थ्योरम 2. ओके, बाय थ्योरम 2, बाय थ्योरम 2. So this is refinement, this is finer than this P, so it means that जो lower sum जो होगा that will increase. So this is less or equal to this, और जो upper sum होगा वो decrease होगा. Okay, you should first write F then P. Okay, it's FP actually, FP. This is FP. Then this will decrease, is less or equal to this. So S star, let's write here Q, because P and Q is refinement of Q also. Also by theorem 1, फॉर द पार्टीशन P यूनियन Q, कि कोई भी फिक्स्ड पार्टीशन आप लीजिए, वहाँ से आप ये कंक्लूड कर सकते हैं, लोअर सम ऑफ F विथ रिस्पेक्ट टू दिस फिक्स्ड पार्टीशन इज ऑलवेज लेस और इक्वल टू द अपर सम ऑफ द F विथ रिस्पेक्ट टू द सेम पार्टीशन. द पार्टीशन इज सेम, आपको अब डिफरेंट पार्टीशन के लिए प्रूव करना है. नाउ लेट अस स्टार्ट विथ लोअर सम of P. You have to show that this is less or equal to upper sum of with respect to Q, but this thing is less or equal to lower sum of F with respect to the partition which is the finer than P, but this thing is always less or equal to the upper sum. जो भी आपने लिखा है ये वाली inequality, since the upper sum is decreased, so it's less or equal to S star FQ. अगर आप इनका नाम भी रखना चाहोगे, इसका नाम 1 रख दीजिए, इसका नाम 2 रख दीजिए, और यहाँ से जो आपने लिखा है इसका नाम आप 3 रख दीजिए. तो फर्स्ट जो आपने यूज़ किया इट्स बाय 1, और जो सेकंड आपने यूज़ किया इट्स बाय 3, और जो फोर्थ आपने यूज़ किया इट्स बाय 2. सो दस लोअर स्टार is less or equal to the upper star. So thus lower star of F is less or equal to the upper star of F with respect to the partition Q. ओके, आज हम इतना ही करेंगे. इसको आप अच्छी तरह से देख लीजिए. तो तो कल हम इसमें रीमान इंटीग्रल फंक्शन को डिफाइन करेंगे. We will define integral function. Then we give the Riemann's criteria for integral function and Dot-Box theorem. We'll discuss after that. And finally, actually, जो आपका main result इसमें, that's very important theorem. That's called a Lebesgue-Vitali theorem, which states that a function is Riemann integrable if and only if it's continuous almost everywhere. So that's very important result in this section. And you will also see that after that you will see that every Riemann integrable function is Lebesgue integrable. That we'll also do. And finally, we have to see the fundamental theorem of calculus. Okay, so it will take 3 to 4 lectures. I think next week we'll complete this